here today. Vivek is a professor at MIT. He told me yesterday, he tells people he's not an operations manager. He's an applied mathematician. So we have a...
That was only for your ears.
Oh, sorry. And for everybody you tell.
I don't even know it, and it's like I said, applied mathematician almost is a joke. Because we do applied things, and there's some math involved.
Some math. The thing is, right, Vivek, I guess I'll give a brief history. He worked a lot on approximate dynamic programming for revenue management, but since then he's done a lot of stuff beyond revenue management. He recently delved into matrix completion, tensor completion, most recently with the uncertainty quantification for that. So he's done a lot of stuff. He's done some really cool things in applying all of these things, had a startup implementing it, got bought off by Nike. And today he's going to tell us about, I think, about digital experiments in an online market, online platform, and how to do it well.
Thanks,
Vivek.
Yeah, thanks so much for having me. It's a real pleasure to be here. Hopefully, I realized I should have set up a clicker. We'll just tap on this. So thanks so much for having me. It's a real pleasure to be here. As I was just saying to Nathan a second ago, the last time I was here was 10 years ago in the old Google building. Nice to be back exactly 10 years later. Nathan, I imagine you were a graduate student then, and I had more hair. So, well, I had hair. Maybe that's a better way of saying it. Okay, so I'm going to talk about this problem of oh, thanks. Appreciate it. So I'm going to talk about this problem of what we call Markovian interference. I'm going to talk about an estimator for this. This is joint work with a few people, Andrew Lee, who's at CMU, Tianyi Pan and Andy Zhang, who are at MIT. And this is, the lion's share of the credit is definitely on the right-hand side of this, Tianyi and Andy. And among those two, this is actually Andy's job market, a part of Andy's job market work. So he's kind of the expert on sort of all of this stuff over here. Before kind of getting into it, I'll sort of say the theme over here, whereas the talk itself is about experimentation. Whereas the talk itself is kind of about experimentation, the high-level sort of theme that I actually have in mind relates more to policy optimization than anything else. And I'll try and make that connection clear, okay, as we go along. All right? Okay, so let's start with this problem. Okay, so let's say here, and I want to assume no background, okay, for everything we're going to do. So first order, right? So hopefully, everybody comes along for the ride. Okay, so let's say I'm eBay, right, and I'm optimizing my search engine, right? So, by the way, on a commerce platform, the search engine is probably the #1 thing that gets experimented with, right? There's typically an experiment going on with the search engine sort of internal ranking or something like that constantly, right? So it's not uncommon for this to happen. So let's say I'm doing some sort of search engine optimization, right? And I want to figure out whether this new kind of ranking I have is valid. Okay? So a simple way maybe you might think about doing this is you run an A/B test. Right, you randomize, users into test and control. One user, test users get the test ranking, control users get the other one, and you measure conversions between these two, the difference in conversion between these two groups. Pretty straightforward. So this looks like it should be just fine, and as it turns out, it's not. So Blake and Cody, actually, as it turns out, David Riley. Were at eBay at around this time, and they were sort of looking at exactly this problem, right? And here's a quote from what they said. Yeah? So consider the example of what I just said. Consider the example of testing a new search engine ranking algorithm which steers test buyers towards a particular class of items for sale. If test users buy up those items, the supply available to the control users declines. Okay? So they're sort of saying that, well, there's interference over here. Right, the test units and the control units effectively interfere with each other because you have finite inventory of whatever product it is that the search engine steers people towards. By the way, this is this is much older than 2014. This observation in the context of internet experimentation. In particular, David Riley has this sort of 1999 paper on selling magic card. Magic's a game, right? For the nerds in the room, but it's a card game. And so David's thesis, actually, when he was a PhD student, was one of the first theses thinking about running experiments on the internet. And he kind of observed this roughly the same effect in this paper that's in the AER. A fun fact is that when I was a freshman, I was David's RA. And I helped, actually, he was very big on writing these, building these experimental platforms to see how people behave. And I helped them build a few of those things. But I wasn't aware of this work until much later. I wish I was aware of it. So what happened in 2014? Right? Like why write this paper in 2014 if this has been around and people have been aware of it for so long? So then really the point that these guys were making was that actually, sure, there's a bias, but actually you have to care about the bias. Right? The bias can be often large enough that it kind of changes the sign of whatever it is that you're estimating. Okay, so your conclusions can actually change. That's the kind of the context in my mind of what these guys were saying. Okay. So it matters in some places. Okay, so eBay is not like the only place this happens. This happens all over the place, as it turns out. So Andy Zhang and I and a couple others are working with ByteDance, doing the socially amazing work of making TikTok more engaging, right? And yeah, it's a terrible thing to do. But anyways, so tweaking lots of different things, right? And here's one of the things they're tweaking, right? So you can tweak really how you present a video. There are all sorts of little things, right? So I imagine, maximize the dopamine rush from pulling up these videos, right? So you can tweak videos in a variety of different ways. The same sort of thing happens, right? Essentially, consider yourself as you get shown test videos and control videos, right? These videos actually impact each other because presumably you have limited time or limited attention span. And that's sort of an interference that happens essentially on the individual sort of user level, right? But you can have similar things actually happen on a population basis too, for other sorts of things that they're trying. So for instance, they're also trying to do things very similar to eBay, right? Related to essentially how they recommend things or they do retail these days. So what retail tricks work and what retail tricks don't. They also have this sort of thing happening over there. So this is an issue. This is an issue for those guys.
Just I can ask a question.
Yeah, of course.
So is it so? Of course, the main mechanism here is that you use up the good. So if I buy the good on eBay, no one else can get it.
Yeah.
Therefore, that's how the interference is coming, at least in these examples.
Yeah.
Or I watch a video and I don't have budget to watch enough.
Yeah.
But I think on eBay, then there's many unique items. I think yes, there's only one of everything to be sold.
Yeah.
And you start doing Amazon, you're talking of thousands of everything. The effect might be a lot, and TikTok minutes.
Good. So let's talk about this one. So actually,
and also for TikTok, because your budget, as far as I don't do too much. Okay, I do a lot of TikTok these days, but that can be a lot. Like you can spend 90 minutes. I think the average viewer is spending like an order of 400 minutes a week or something like that. So that means there's not that tricky, and each video is less than a minute, so it's not that much interference.
Yeah. So that's right. But the thing is that the treatment effects that you're trying to get at are also really small, right? So essentially, you're not expecting to find something that's going to change engagement by 10%, right? That's going to be a disaster for the world. But you're basically finding treatment effects that are themselves tiny. And so you're right that the impact of the interference is small, but as you'll sort of see later, it's very often on the same order. And that's kind of the point of this Blake and Coe stuff too, right? So it was very surprising, right? Yeah. So the Blake and Coe paper was a great paper. It's an empirical paper, right? And what they did is they showed a bunch of different experiments that they tried, where they concluded, look, this is going to be
that was eBay.
That was eBay, right? That's going to be a point something percent lift in overall conversion. And so, well, actually, we didn't get the sign right when we actually rolled it out. What we see on TikTok is something similar, by the way, right? That is to say, if you kind of are naive about the whole thing, you conclude one thing. And it's not uncommon that if you're not naive about it, actually, it turns out you might have gotten the assignment, right? And again, it's because the impact itself is actually really small. I actually had the opportunity to sort of give this talk at Amazon in the group that's actually experimenting. So they have several experimentation groups. And there's one group, so there's an experimentation group that works on kind of front-end stuff for Amazon. And there's a separate experimentation group, I'll get you, that's kind of thinking about really, how do I experiment on fulfillment algorithms at my warehouse, right? This is a very nasty kind of problem, right? Because it's not really clear how to do this, right? Like, it's not clear how to cut up the system. Like, yes, I have 140 warehouses, but it's meaningless for me to talk about, implementing the algorithm at a warehouse and not the other warehouses, and things of this nature. So even getting to kind of how to construct the test.
Yeah, so I guess in a
hard.
B2B setting, when you don't have consumers, you won't have enough to do A/B anyways. Like you probably have to do something else.
Yeah. So hopefully, what I talk about in a second, we'll try and formalize this and come up with a language for how to think about all this, right? Go ahead.
Yes. Feel free to say it's not the point of your comment. All examples I've seen of this is where you get the sign right, but you just get the magnitude wrong because like the crowding, right? Like you make an experience better, that like the treatment gets.
So I think that's the point of the Blake and Cody paper, but the sign is wrong. Okay, so if you look at this
I
paper,
thought I remembered it as the sign was right, the magnitude.
I think you misremembered.
Okay.
Yeah. So there you're wrong. But I think that's the point of the paper. Okay, that the bias is basically on the order of the treatment. Right? And certainly, I mean, what we're seeing is these places. I mean, very clearly, you can get the sign wrong. Okay. Yeah. By the way, there's sort of, I mean, even if you did not get the sign wrong, right? There's something to be said about getting the magnitude wrong. Because sometimes what I'm thinking about over here is measuring sort of the ROI of like the implementation vis-a-vis the cost. And if I exaggerate what the ROI is, I'm going to get to the wrong decision. I mean, look, at a high level, we can debate about whether this problem is important or not. I can tell you at TikTok, we think it's important enough to have 100 people working on it. Amazon, there's similar size group of people. Yeah.
Just before we move on to the technicals, like a high level, you can talk through kind of when the signs are wrong. Does it have to do a lot with misalignment between the thing you want to test and the thing you might be pushing? So for example, the TikTok thing, either the budget is not saturated and you're just pushing them to watch more, good. Or the budget is saturated and it's just zero added value. Or is the issue that you're pushing the videos, they give you less revenue or what?
I think I see what you're saying. Yeah, so sometimes what ends up happening is this is a sort of a dynamical system of it. And what you end up doing is a decision that you're making on one guy, which might be sort of a long-term payoff for the system, right, gets essentially piggybacked upon by like the other guy, right, where you didn't make an investment. Okay, so there's some structure in the system, not necessarily an inventory constraint or anything like that, right, but it's just the dynamics of the system where the long-term impact of a certain action, right, the benefits of that, for instance, or the price of that is borne unnecessarily by people that shouldn't get the advantage or disadvantage of it, right? So that definitely happens. And that, by the way, is more common in this sort of setup, where when you kind of think about like trying to come up with, how do I try out some new policy at this warehouse? And I try to say, so one of the things they try to do literally is to say, you know what, I'm going to run the policy on this set of SKUs and not on this other set of SKUs, right? But obviously, you can't really do that because what it results in is kind of the quote unquote alignment thing that you're talking about. Okay. Okay. So how do you do that? How do you deal with this? Right? How are people dealing with it? So there's two ways of dealing with this, right? One is you can sort of think about like non-trivial experiment designs, right? Don't do naive A/B testing. Do something smarter. And so one thing I could do is some kind of clustering in either time or space, right? So for instance, clustering in time would be I run a switchback of some sort. Right? The whole system runs on one thing, and then the whole system runs on something else. I can think of doing, if it's a social network, and one part of the network doesn't really interact with the other part of the network, my colleague Dean Eccles thinks quite a bit about, how do I kind of cut the system up, right? To get some sort of clustering in space. There's a bunch of things you can kind of do. There's a bunch of things you can kind of do over there. So often when you sort of do this, at least the places we've kind of sort of said, well, why not just stop here? Why not just do a switchback, right? The challenge to that is if I'm doing a switchback, typically I'm turning on whatever experimentation policy I have for the entire platform, and that's something sort of unacceptable, right? Now you can sort of try and cut that up further and say, no, I'll turn it for the platform, but I'll only do it in one city, or something like that. But these things actually, but then you start paying the price of your experimental units of your course, something like that. Okay, so it's not really that clear that you can sort of do a switchback in some of these examples. Certainly the TikTok example. And with respect to kind of cutting up the thing in space, at least in the TikTok example, really again sort of right, it requires a very distinct mapping of people saying, oh, these guys only watch this and these guys only watch that. Not really clear what they're saying. Another approach. Sorry.
You say switchback. Why not just go turn on the other way around? So you expose the policy only to a treatment group.
Yeah.
And then.
Oh no.
But difference we can still do. Right?
No.
Why do you say only switchback?
Good. So I think the challenge of here is how do you think about that treatment group, right? Because the treatment group. So as soon as you say treatment group and control group, you're assuming these units have nothing to do with each other.
Got it.
The thing over here is
it has to be clustering in space.
Yeah, and then clustering in space on TikTok, like kind of hard to do. Then there's this sort of really nice idea of multiple randomization that Ramesh and Gabriel and Hannah worked on at the same time. Pat Bahari at Amazon has sort of worked on. Roughly speaking, it's more of a heuristic, right? And the rough idea over there is thinking about potential outcomes in sort of the grandest of senses, right? Where basically I'm thinking about like the entire vector of of treatment assignments and trying to sort of say there's enough structure in my problem that I can make some kind of conclusion, right? About getting the treatment effect right? So for instance, in the Bahari work, which by the way it's entirely heuristic, there's no theory, right? But in the Bahari work, the whole point is that again we think about potential outcomes. It depends on the entire vector of treatments, but I'll make some assumptions on the regularity of the outcome with respect to the interventions, right? And that hopefully lets me adjust my observations, right, in the right way, construct a propensity score, something like that. Okay, so that's sort of one approach. The folks at Amazon are kind of really working hard on getting this to work in the fulfillment example that I talked. But again, as I said, there's no theory. The other thing you could do is you can sort of stick with sort of a naive design, right? Just do an A/B test, right? Like the bad thing, right? So I just do the bad thing, right? It's the simplest thing I could do. And after I've done that, I try and estimate in a clever way, right? So what are the extreme points of that? The extreme points of that are, one thing you could do is sort of like off-policy evaluation, right? Which I know there's experts in the room, but at a high level, if you're not familiar with this, right? Like all this is essentially a very sort of fancy form of importance sampling. Maybe that's one way of if you've never ever seen this before, that's what it is, right? But I could try and do off-policy evaluation. There's various ways of doing this. You can do it in fact in a way where it's unbiased, but potentially you pay a price in terms of variance, right? There's nothing excluded. And then you could do what you were alluding to, which is actually not uncommon. Right? Forget about it, right? Just basically ignore the bias, right? I'll literally do the A/B test. When it comes to interference, what I'll say is, I don't care about it, right? I don't want to think about it. And actually, yeah, in practice, this is also, I think thus far has been reasonably common, but it's getting less and less common as people chase smaller and smaller treatment effects. So that's kind of the, let's call it, 50,000 foot level sort of overview of what one might do in this setting, at least what I want to do. Okay. So I want to focus on this piece, I don't want to focus on building a special experiment design for this particular talk. I said, I'm just going to do A/B testing. All right. So basically, you randomize your units, although there's interference. You're going to randomize your units between test and control, and hopefully, at the end of this, you do something clever, right? That gets you a reasonable answer. So in particular, the big question. This is actually the whole talk in English. Okay. So you can fall asleep after this, or if you've not already fallen asleep, right? So in English, this is what I'm asking. All right. So what I want to ask is, what can we do when we do an A/B test and have a limited experimentation budget? Right. So I have an A/B test, and I can't run the A/B test forever. Right. So making that question a little bit more meaningful, the way I'm sort of thinking about it is, and I'll make this more clear as we go along. You sort of think about the naive approach, right, which is do an A/B test and then just literally look at a difference in means. That's sort of one extreme of the bias-variance curve. Another approach maybe is doing off-policy evaluation. And I sort of, in my mind, I think about these as two extremes because if I sort of think about naive, the variance is pretty good. And I'll characterize what I mean by variance is pretty good in a bit, right? But not surprising, right? The variance of this thing is not bad at all, right? But the bias sucks, right? At least that's the point, that's the subjective point we've been making so far, and we need to sort of think about why the bias might actually suck, right? On the other hand, if I think about OPE, that could be unbiased, even, right? But if I went after something that was unbiased, chances are I'm going to pay a price in terms of variance, and that price will be so large that it doesn't make that sort of amenable to an A/B test where I have limited experimentation budget. So the question I want to ask is, if I view those as two extremes, is there a productive bias variance? Okay, and is there a nice, productive, simple way of exploring that bias variance? Yes, that's right. And the answer to this, just one second. All right, the answer to this is I'm going to offer an estimator. So I'm going to call it the differences in Q's estimator. It's called the differences in Q's estimator, building on the notion of differences in differences. Okay, with Q functions playing a certain role. And here's what we're going to show. We're going to show, first of all, this estimator has sort of provably second order bias relative to a natural parameterization of the treatment effect. Okay, so that's point number one. The second thing I'm going to show is that this has exponentially smaller variance than optimal OPE. So you pick an optimal unbiased or even asymptotically unbiased OPE algorithm. This will have exponentially smaller variance in the size of the state space. And then finally, I'll show that in a bunch of experiments. Unfortunately, we didn't get to a place where I could show you the TikTok stuff. I would have loved to have shown you that, but I can't. But instead, I will show you something real, right, at real scale. And so what I'll do is I'll show you some real scale stuff where this does pretty well. Okay, so that's the talk in a nutshell. So you have a question.
Yeah, as you know, I'm not from this field, and a lot of these abbreviations I don't even know. But let me ask you something. What's the objective function here underlying this optimization? Are we maximizing ROI, or are we looking at preferences of individuals, or is it a pure stochastic dominance argument? How do you come up with optimality in this kind of? And
so I think you got to give me a second. No, that's fine. I think that's a fine question. So why don't we do this? I see where your question is coming from. Actually, I think I'm going to formalize the problem in a second. And so give me, I think either one or two slides. And if the problem's not clear, then I'll come back to what you're asking. Okay? But in English, right? In English, the idea is very simple. In English, the idea is I want to get the sign right. Right? Like I'm going to try something new, and I want to get the sign right. Okay, I want to know whether if I actually did this in my system, it would actually work the way the way my experiment suggests it's going to.
But you may not know it's the best.
No, I may not know.
Especially with the
exactly. Okay. Okay, so let's formalize this. Okay. All right. So here's a nice simple formulation. So I have some dynamical system with a state space script apps. All right. The action space over here is either I do whatever the incumbent thing is, or I do my new thing. right? So at every point in time, either I show you the old version of the search engine or the new version of the search engine, right? 0 or 1. Okay. A policy pi is simply, right? You know, an a-value random variable, right? Given the state you're at, either you do 0 or 1, right? With every policy pi, I'm going to associate a kernel, p pi, right? So the transition matrix of the underlying chain. I'm going to use rho pi to denote the steady state distribution of that chain. Okay. And in any single period, I have some cost function r. You should think of RSA as big random. Okay, so that's the setup. And given this setup, I can obviously define average cost. I'm defining it implicitly, making some assumptions about the system being unichain and things like that. But I encourage us to not think about this technicalities. We can if we want to, right? I'm just sort of going to say take a limit. I care about average cost. Okay. Okay, so what do I want to do here? And this should get, now we're going to get to your point, your question is your formalizing the grid. Okay, so this is our task. It's actually really simple. So we have an incumbent, what I'm going to call an incumbent chain, which basically is the old way of doing business, right? At every point in time, you show simply the old search engine. It's how you were doing business, right? Then I have what I'm going to call the intervention chain, which is basically, presumably the new way of doing business, right? At every point in time, I show you the new search engine, right? I'm going to call that pi1. So if I think about pi0, what does pi0 do? At every state, it takes the action 0, old search engine. pi1 at any state takes the action 1, new search engine, right? And each of these is associated with some average cost, right? Or average reward, however you want to think about it. Lambda 0 and lambda 1. Okay? Now, what you care about estimating at the end of the day, what you care about estimating at the end of the day is the difference between lambda 1 minus lambda 0. Okay? That's our goal. Right? This is what I care about estimating. So why is this not trivial? It's not trivial because the data I'm going to have is generated by neither of these chains. Okay? So the data I have is going to be generated by some third chain. And what is that third chain? In this particular case, because I'm focusing on the simple A/B testing setup, and just for notational simplicity, I'm going to make 50-50, right? Half the time I flip 1, half the time I flip 0. So that chain has a transition matrix that's simply the average of these two transition matrices. You know, that's my problem. It's a very, very simple problem. This is what we got here. Questions on the task?
So yeah. Why are we? You told us not to think too hard, but why model it as a dynamic system? Is it what's practically what is kind of by the time?
That's a great question.
Just kind of average across.
No, this is a great question. So let's actually look at some of those examples, right? So in the TikTok case, they actually have a dynamical system model of how a user behaves, right? So
like I don't know what the mark is.
Yeah, it's highly proprietary.
Okay. Yeah. So are you saying dynamic? So what is dynamic? Like they are responding in real time to what you're watching?
It's literally this, right? So in concept, they have some descriptor of your state, right? And they're going to guide you moving forward, right? Based on the state they think you're at, right? And they model your evolution as something like this model, right? So that's that. But you know, like if you think about Amazon, right? And you think about running a warehouse, it's not the same story, right? The state is kind of like all my inventory of all of my stuff, how much capacity I have left, how many trucks are showing up, whatever, and that system evolves, right? Now, one thing over here to bear in mind is that, like in the background, there's some very complicated policy running, right? Like, oh, send this here, this there, whatever. And we're kind of focused on one aspect of that, right? Which is the 0 or 1. Imagine this as like some complicated policy parameterized by some parameter theta. There's theta 0, which is the old way of doing things. Theta 1 is the new way. At least that's how I do it. Okay, that's the dynamical system. Okay, so that's the problem. So let's start with the obvious thing, right? So we said, hey, there's bias, blah, blah, blah. Let's make it clear why there's bias, right? Let's wrap our heads around why there's bias, right? Yeah, so this is the obvious estimator, right? The 95th. Right? I look at every time I use 1, I look at the average reward there, I subtract the average reward of every time I did 0. This is obviously biased. And by the way, I'm calling this low variance. This is low variance because at some level, the variance of, I could get zero variance, right? But just say zero, right? So there's not much content in saying low variance yet, right? This is low variance in the sense that the variance over here is not going to scale with how complicated my state space is. The first order, right? I can in many situations get O1 variance, right? I mean, not many. R is bounded, for instance. I have O1 variance. Okay. So the variance of this thing scales pretty nicely. But obviously, there's an issue here, and the issue is that variance is fine. The bias sucks, right? That's the point I was making earlier in English. In math, what's the issue? In math, it's this issue, right? So let's say I ran this thing forever. Or let's say I ran this, right? I had tons of samples. What's the estimator I'm computing, right? So what I get is this sort of weighted average, right? So essentially, I'm looking at the rewards under the new policy minus the rewards under the old policy, except weighted under the steady state distribution of that experimentation chain, rho 1/2, right? And in fact, what I want is something like this, right? What I actually want is the rewards under the new policy weighted on the steady state distribution of the new policy minus the rewards of the old policy weighted on the steady state distribution of the old policy. So the point is there's a distribution shift, and that distribution shift presumably introduces bias. Okay, so let's think a little bit more carefully about that bias. All right? So in thinking a little bit more carefully about that bias, okay, I want us to think about parameterizing the impact of the treatment as follows. Right, so these are parameterization. Okay, so think about the parameterization as follows. At every state, right? Presumably, if I took action 1 versus action 0, and it didn't impact my distribution over next states, there's no problem, right? I'm done, actually. The naive thing would be just fine. So if there is interference, it has to change my distribution over next states. Okay? So what we're going to say is, let's parameterize how much it can actually change your distribution over next states, because this is really what matters. Okay? So I'm going to say, hey, let delta, right? Let delta sort of parameterize how much you can change your distribution over next states by using action 1 vis-a-vis action 0. Okay, so let's parameterize things that way. If this were the case, right? It's clear that essentially the steady state distributions can't be different by more than delta. Okay, so your steady state distributions can't change by more than delta, and as such, your ATE is going to actually be order delta. But you can come up with plenty of examples where the ATE is in fact theta delta. Okay, so in particular, I can come up with examples where the ATE is theta delta, and the difference between the ATE itself and this naive estimator that I was talking about earlier is larger than that. So you get the sign wrong. Okay? So essentially, all I'm sort of saying here is I'm just formalizing what we talked about earlier in English, right? That basically at the end of the day, if you do this, your treatment effect is delta, you did naive estimation, the bias is going to be order delta. Okay. So here's how I want us to think about this, okay? Like as a mental model. But if just imagine this two-dimensional cartoon picture, okay? So I'm going to put bias on the y-axis, variance on the x-axis. All right? So this naive thing that we just talked about, right? This has variance that's order 1, right? It has bias that's order delta, and in many cases, bias that's theta delta. Okay? So that's one extreme. Another extreme is I could do something like OPE. Let's say I was doing unbiased OPE. If I did unbiased OPE, by definition, the bias is 0. But the variance is going to scale at least as large as this. Okay, the size of the state space. Now, really, where do we want to be? Right? One way of sort of thinking about where we want to be is let's look at the sort of the circle I get. Right? When I think about the I want the RMSE to be less than delta, right? At the very least. Okay? So imagine I look at RMSE less than, I don't know what I just did. Okay. Let's say I look at this circle of RMSE less than delta, right? The cartoon I want, ideally, right, is I get some sort of, estimator, right? Where hopefully, right, I get into this sort of circle of it. Yeah, that's my cartoon motivation. This is how I'm thinking about the problem. right? I want to figure out like a nice kind of parameterization between these two things, right? Where in effect, I can sort of, get low bias and variance that's small as well, relative to the size of the space. That's how I'm posing it. All right, so the whole game is going to be what can I get from it.
So just a clarification question.
Yep.
So why is it exactly a circle? The region where are less than that?
It's a bias square plus variance square square. Okay. That's all I mean. Okay. Yeah. Sorry.
By OBE, what do you have in mind? First, I don't know this. I know the more economic side. OBE means counterfactual, right?
No. So Nathan's the expert on this. So basically,
OBE is not a counterfactual. It's not like you have a model and then we can do a counterfactual.
I'll just tell you what it is, right? So I'll just tell you what it is. So you remember how earlier we said we were getting all these rewards, but under the wrong steady state distribution? So the idea is to somehow correct for the fact that you have the wrong steady state distribution. There's various flavors of correcting this. There's a zoo of algorithms you can use. As opposed to thinking about that zoo of algorithms, when I talk about it, I'm instead going to look at like Cremers-Rao bounds. I'm going to say, well, if you had the optimal algorithm, what's the best you can do? All right. But be aware of the fact that there's a whole zoo of algorithms that you can use, right? And the problem is much more general. That problem is much more general than what we're talking about. Okay. That's it.
I get it. So the best algorithm could never be better than this.
Yeah, that's the point. And in fact, I'm actually being a little fast and loose. So I'm calling this the size of the state space. And in fact, it's actually worse than that. It's something else, which I'll show you later when we make this fourth one. Okay. Okay, so now I want to talk about my estimator, right? So this was the old estimator, right? There's differences in rewards. I'm going to make one like superficial tweak to this, okay? A little bit comical, which is I'm going to take out those rewards, and instead I'm going to put in Q functions, okay? So let me just say what these Q functions are in the first. I'll define what a Q function is in a bit. For the folks over here that know RL, which I imagine is the vast majority, you know what it is already. But what is this Q function doing? This Q function is basically trying to adjust at some level for the fact that when I take this action, not only do I get a new reward, but you're now going to dump me into a new state, which other people downstream actually take advantage of. It's the exact intuition that Nathan was talking about at the start, about really kind of changing the starting point for the guy that comes after you. Now, the Q hat over here relates to the fact that I'm going to have to compute these things from data. So at the end of the day, I don't have a model or anything like that. All I have is state, action, reward, state, action, reward, state, action, reward, and I need to compute some estimator. So we're going to need an estimator for everything we'll talk about. Assume that I'm using an algorithm called LSTD, okay? So I'll use LSTD, and I'll compute these Q functions. What is the sub 1/2? That's actually really important, right? This is the Q function computed under the experimentation policy. Okay, that's really important because that Q function is a lot easier to compute than the Q function under something else. Okay, so that's all we're doing. Right? So the differences in Q functions. Okay, what can I say about this? What I can say about this is the following things. All right. First off, the bias of this estimator is second order. Okay, so the bias is order delta squared. All right, that's point number one. Actually, the ideas behind this are far more general and interesting than just this problem. And after I talk about how this works, that's where I want to kind of steer all of you guys. Okay, so I want everybody to get like a theoretical idea out of this as well. And so I'll get into really what's happening over here. Okay, so this estimator is second order bias. That's point number one. Second, the variance of this estimator is also low. Okay, in particular, it scales like roughly log the size of the state space times the variance of that naive estimator. Now, right, it's not independent of the size of the state space, but the hope is that this is a very mild scaling with respect to the size of the state space. And then finally, the variance of an optimal unbiased estimator is going to, in general, be exponentially larger than this estimator. Okay, so there's three facts, right? And on that picture, this is how I think about that, right? Basically, At the very least, there's this one point. Now, it turns out, by the way, the result's much more general. It turns out there's a whole bunch of these points where, as opposed to delta squared, you can get delta to the k, and then pay a price that roughly scales like log s to the k. Okay, so there's a whole family of things that you can get. But for now, let's talk about differences in Q functions as well. Okay? Okay. So, yeah, Mas.
How are you estimating Q functions?
This is what I said earlier, LSTD.
LSTD means like, are you using
It's
functions?
batch LSTD, right? Because I've got all the data from the trajectory and I just solve the batch.
No, I think he's asking using like a linear function approximation.
Are you using tabular?
This is tabular. Like I'm not talking about any approximations yet. It's not tabular. I'm not talking about any. That's an orthogonal thing at some level, right? So in particular, as soon as you do function approximation, you're gonna get another layer of bias, right? Because you're getting the two functions wrong. And so that, by the way, I mean, I'm not sure if there's, at least for this level of generality, a productive way of doing that. But it's certainly a very important question, because in practice, if I have a massive system, I'm going to need to do this. And so later on, I'll show you an example on the Uber simulator, which is very high dimensional. And I'll show you what happens in the Uber simulator, okay, with this estimate. But in practice, in addition to the tabular thing, you probably have some sort of approximation, some sort of function approximation, right? Some actor created point. Sure.
Yes, thank you.
Good, great. Okay, so first of all, how well does this work, right? Before talking about theory. So here's what I'm going to do. I'm showing you a tiny experiment. I'm going to do some theory, which I'm excited to share and talk about. Because I think there's something cute over there that's like interesting broadly. And I'll show you another large-scale experiment. But the first experiment is a toy experiment. And I deliberately picked an experiment that somebody else proposed. Okay, so it's an experiment proposed in this paper by Ramesh, Hannah, and Gabriel. I'm going to set it up exactly the way they set it up, right? And so their experiment is like basically this is their like sort of like caricatured model of Airbnb or something. I don't know. They have a story, right? But at the end of the day, it's a one-dimensional Markov chain. Okay, and all you're doing on this Markov chain is basically your action kind of controls the probability you go left. And ideally you want to be left, you want to go left. Okay, the more left you go, the more money you make. That's roughly the flame. Okay? And so in essence, the 0 and the 1, for zero, the 0 policy, delta is basically 0. The 1 policy, well, there is a delta. Okay, that's the idea. Right? So that's literally their setup. And I'm going to try a few different things, okay, over here. So we're going to try naive, which is the dumb thing, right? Averages on both sides. I'm going to try a variety of different OPE estimators that have been proposed for this average cost setting. One of these is unbiased. The other one actually is not unbiased. There's like a regularization involved, right? But I'll try both of them. I'm going to try what these guys proposed and recreate what was exactly in their experiments. By the way, I'll say more than that, but there's two flavors in their paper. I'll talk about that, and I'll talk about the differences, right? So here's the picture, right? So first of all, in this paper, they only report like sort of one point in time, right? And that's a little weird, right? Like you want to see what the trajectory is. So I want to show you the entire trajectory as well, right? So essentially what I have on the x-axis is how many samples do you have, right? How long are you running the A/B test, right? And on the y-axis, I have RMS. Okay, so bias, because not all of these, some of these are biased, some are not biased, so I'm going to bias squared plus root, right? So let's actually look at these, okay? So naive is this sort of the dumb thing, right? This guy over here. All right. The things that were proposed by these guys, the TSR stuff, are the dark green line, and then this sort of, I don't know what this color is called, but this line over here, right? Right below, the penultimate line. I should note that this second policy, in effect, cheats. This TSR2 or whatever cheats, because it actually looks at certain parameters of the problem. And then in effect, it tunes against those parameters, which makes it a little bit shady. But nonetheless, I've used exactly what was done, right? The red thing is differences in Qs. It implemented exactly the way I said I implemented, right? It's LSTD on the entire sort of batch, and that estimator I talked about. There's 0 tune, okay? And then there's sort of OPE, which the sort of non-regularized OPE kind of sucks. And the sort of regularized stuff, which is this sort of TD kind of variant, does somewhat better, but again, not super well. Okay, and then the red thing, as I said, is this differences in twos. So this was kind of the first thing we did before we tried to prove anything, just to see, hey, this is something meaningful going on over here. And this was sort of what kind of encouraged us to move forward. Hey, did you have your hand up?
Yeah, but it's not about this experiment, so I'll let you.
Oh, perfect. Okay. So here's what I want to do next. Okay. So before I talk about a real experiment, I want to talk about a little bit of theory. All right. So in particular, this theory part that I'm going to talk about is actually interesting beyond any of this experimentation stuff. Right. It's more about a dynamic programming. So in particular, I'm going to develop a novel Laurent expansion for the average cost that I think is broadly interesting. All right, so I'm going to spend some time on that. I'll sort of say the results for variance more formally than I have so far. And then I'll show you an experiment that's like, yeah, that's what's coming next. Okay, let me actually pause here for questions. Go. I know you want to ask, so I apologize.
No, okay, but maybe you'll get to. You said something about optimization at the beginning, so maybe you'll get to.
See this one?
Maybe you'll get to it because you mentioned something about optimization at the beginning. But you know, this ATE thing is looking at. It's like a choosing according to your difference in Q estimators. It's like a policy improvement step because you're rolling out the 1/2 later.
Yeah.
You're just choosing what am I going to do immediately. If
Sure.
one, I'm going to do 0.
Yes. Sure.
And so, if in the end of the day, A/B testing is just for improving the system. Look, who cares about estimating? I just want to improve the system, keep improving it.
We're in violent agreement with each other.
Yeah.
So in fact, I think the theory that I want to focus on is focused. It's focused almost on policy optimization.
Yeah.
As opposed to anything else.
Okay.
And so if we talk about policy optimization, right? I think the meaningful thing to think about over there, at least the thing I'll claim is meaningful, at some level is sort of like a radius of convergence, which I'll make formal in a second. So if you're thinking policy optimization, stay with me for like a few slides, because that's exactly what I want to talk about. That's my mental model.
Okay.
Why are you smiling?
No, because I'm thinking, but you're still going to go with one experiment. I'm thinking like if I'm just thinking this approach is very inspiring. Of don't just run A/B tests. Keep running A/B tests. Keep doing a policy improvement step. You'll get to a really good policy.
Yeah, I agree with you.
Okay.
Yeah. So dude, you're preaching the choir, right? So I think, I've had these discussions like TikTok, right? And I think you're exactly correct, right? Why stop with one step, right? And very often, by the way, these experiments boil down to changing some crazy hyperparameter or something like that. Sometimes they don't, right? So for instance, like right now, the experiment that the guys are working on is like a change in codec or something like that, right? Where they, like if the video looks better, so it's not necessarily a hyperparameter change. It's like kind of a policy and it's expensive to do, right? For a variety of different reasons. So that doesn't necessarily fit. But I think there's plenty of things where it's like, I'm basically changing a hyperparameter, right? In which case, right, keep going, right? Do this now, see what you get, and then keep going, right? I totally agree with you. So, but the theory I'm going to talk about, I think the theory supports that, right? This thing I'm going to develop in a second. All right? Okay. So let me actually now say something theoretically, hopefully interesting. All right. So I want to get everybody on the same page, right? I want to define two things, just to make sure that they're defined and clear to everyone. I'm sure that you guys already know this, but I just want to make sure they're defined. Right? So the first thing I want to define is a differential value function, right? And this is the analog to the value function, except that in the average cost case, you subtract off the average cost of the policy. Okay, so I'm going to call that V. And then the Q function in this setting is what? It's simply that you take, the Q function under policy pi of taking an action A at a state S, is you get the reward of taking action A in state S, minus whatever the average cost is, plus the differential value function from there on there, assuming that from there on there you continue to use pi. Okay? These two definitions should hopefully be very familiar to you. If they're not familiar, again, this is sort of the notion of a value function in average cost. This is the notion of a Q function in average. Okay, so that's one piece of background. Hopefully everybody's familiar. Let me talk about another piece of background, which you may not be nearly as familiar with. And in particular, I want to talk about the group inverse of the resolvent of a Markov chain. All right. So in particular, if I looked at square matrices that are not nilpotent, right? So square matrices where rank A is rank A squared, basically. Okay? So that's a multiplicative group. And I'm going to denote by A sharp the inverse element in that multiplicative group. Okay? Now, by Perron-Frobenius, the resolvent of, by Perron-Frobenius, the resolvent of the sorts of Markov chains I'm working with, right, like one irreducible class, et cetera, right? They're an element of this group. Rank A equals rank A squared. Okay, Perron-Frobenius lets you show it. Okay. Right? So what I wanted, so here's the interesting thing, right? It turns out that the group inverse of this resolvent basically contains all of the interesting stuff you want to know about this chain, right? And I didn't know this stuff, but I learned it from this really beautiful set of papers by Meyer, written in the 50s and 60s. Okay, so it's a beautiful object. All right. And by the way, in case you're wondering about how do you actually construct this, right? I talked about this in a very implicit sort of way. You construct this by basically working with the Jordan form. Okay, so you basically look at the Jordan form of this thing and you massage the Jordan. Okay, that's how you can explicitly construct the inverse. Okay, so I've given you a sense of what the group inverse of the resolvent is. So here's two pretty facts. Okay. So the first pretty fact is that this differential value function is simply the group inverse of the resolvent times the rho 1. Okay? And this should look sort of, at least like algebraically, similar to kind of the solution of the Poisson equation if you're solving like a discounted problem. Right? So this is not right? You can sort of argue and say, oh, I can write this in many different ways. But it turns out that writing it this way is actually very informative. It's informative because of the second fact. Okay, so here's this really neat perturbation identity, right? What is this perturbation identity saying? This perturbation identity, and by the way, I'm writing everything over here in terms of 1 and 1/2 and so on and so forth. But these facts I'm going to talk about apply to just general policies.
So R pi is length S, where
Yes.
in each state we take the pi,
Yes,
pi of S actually.
correct. And the expected value, right? The expected value. Yeah. Okay. All right. So now this perturbation identity, right? And by the way, if you read the Meyer stuff, he has a lot of these identities, right? They're beautiful. I could go on for hours talking about this, right? But so there's this nice perturbation identity. What does this perturbation identity do? It relates the steady state distribution under the chain that does all ones with the steady state distribution under the guy that does 1/2. And it's an identity. Okay? It's not a bound or anything like that. It's just an identity. All right. I'm going to make hay with this. All right? So here's how I'm going to make hay. And again, I'm writing this specifically in terms of like the stuff we're talking about over here. But this is like generally interesting in policy optimization. And for the people in the room that sort of like that stuff, this probably gives you bigger radii of convergence, so to speak, than existing approximations. Okay? That's kind of the high level. But okay, anyways, so what are we doing with this parameterization, right? So let's start with these, P1 is the transition matrix under me doing 1 all the time. P1/2 is the transition matrix under me doing 1/2 all the time. And I'm just going to write that as delta times C, right? By construction, C is a matrix whose sort of row sums are bounded by 1, and I've got delta outside it. Okay? So this is my perturbation identity where all I've done is I've just post-multiplied everything by R1. Right? My perturbation identity connected row 1 to row 1/2, I've just post-multiplied everything by R1. Right? But what are the terms over here? The terms are already interesting because this term, right, is sort of the steady state distribution. I'm sorry, this is R1 under the steady state distribution of that 1/2 chain, right? The wrong thing, right? And you can sort of think about this as a correction, except that it's, the distribution is row 1, which we don't like, because we don't have access to row 1, right? What do I do with this? Well, I just repeat the same thing, right? So in particular, this is where I am, and the problematic thing is row 1. Well, let me just repeat this process, right? So what I'm going to do is I'm going to plug in for row 1, right? Row 1 is this, right? Just from that perturbation identity, I want to remind you. So I'm going to plug that in. And if I plug that in, I'm going to get something that looks like this. where the first term is, again, that same steady state thing I was talking about, of R1. The second thing is this weird looking quantity that you can sort of interpret as a policy gradient of a certain type. All right, thanks to that fact I told you on the previous slide. But notice it's under rho 1/2, and it's pre-multiplied by delta. And now I have this remainder term, which is delta squared under the wrong thing, right? Under the rho 1 distribution. And of course, I can keep doing this, right? I keep doing this in this fashion, and you get this, what I'm calling Laurent expansion. All right. Now, to Nathan's point about policy optimization, this Laurent expansion can be used directly, a lot of things like TRPO for policy optimization, except that the radius of convergence here is substantially larger than TRPO, both provably and in terms of experiments. All right. But in our setting, I want to use it for something much simpler. And so what am I using it for? I'm going to just forget. I'm just going to stay at order 2. Okay. I mean, I can keep going, but I'll just stay at order 2. Right. This is what I have for lambda 1. Right. This is the expansion I derived for lambda 1. This is the expansion I derived for lambda 0. This difference is basically the naive estimator. Right. Basically, this first order correction corrects that. Right. And in particular, when I kind of go through that correction, I get to exactly this differences in Q's estimated. Okay. Now, one thing I'm sort of sweeping under the rug is what are the constants in the big O over here? And it turns out that the constants behave really nicely. They scale logarithmically in the size of the space. Okay.
So just to make sure, like to get some intuition, would the next order expansion be the same thing as doing difference in Q's, but the Q is like first one, then 1 half, 1 half, 1 half, 1 half?
No, it's not that. Yeah. Great. So actually, what we're starting, it's not quite this, but the way I think about it is basically what the second order, depending on how you want to count. The thing after this is like building a Q function, except that the one stage reward is a Q function. And that's not what you're saying.
Not the same thing?
No. Yeah. So it turns out they do. Yeah. And I know why you're asking the question too. That was my intuition going into it, but it's not. Okay, so this is what we showed, right? I'm not going to talk about the variance stuff, other than saying, by the way, actually, let me just not talk about this. Because what I want to do is just end with, does this damn thing actually work when you build something really massive, right? So Andy was an early employee at Uber, and so he decided when he essentially built Uber's first simulator. So he built a version of that. By the way, the hard thing in doing this sort of stuff is how do you simulate one day in a reasonable amount of time, right? And this thing, fortunately, can simulate one day of traffic in I think an hour, which is apparently very fast, right? So anyways, we're running sort of a simulation effectively. It's very, very detailed. I'm not going to bore you with the details, except to say that what I'm going to try out is actually tweaking a hyperparameter, right? And the reason I'm doing this is tweaking that hyperparameter introduces very, very complicated interference. Okay, so the hyperparameter changes the dispatch algorithm, right? And it decides whether or not to push a new cab into the mix. All right. Now, obviously, if I push a new cab into the mix, I take a hit on what I'm making on that single ride, but presumably downstream rides get the benefit from this, right? And so there's pretty complicated interference, when I do something like this. So he tries out several of these things, and there's sort of a natural threshold of it in this parameter that is Q. Okay, so starting out with 2 parameters, right? There are 2 parameter choices. Oops, what am I doing? There's 2 parameter choices where you actually don't want to do this. Okay, in particular, the true average treatment effect for the first parameter choice is a minus 4.6% decrease in profit. For the second one, it's a minus 1% decrease in profit. What you see over here is what these various estimators estimate, the same set as earlier. And what you see is that the thing in red, this DQ stuff, is closer to the actual average treatment effect. Now, to Nikhil's point, at the very least, all of these get the sign right? They're negative in all of them get the sign right. This one basically, really overstates how negative it is. This one gets it closer. But it turns out that there's a choice of this very natural dispatch parameter for which the treatment effect is actually positive. right? And over here, what you see is that these guys continue to get the sign wrong. This does not. Okay. So just to summarize, I'm sorry for going a little bit over time over here, right? I talked about this problem of interference, right? Which I call sort of temporal or Markovian interference. I introduced a new estimator, which, right, simple, sort of differences in Q's. The bigger picture from this estimator is actually what's underlying all of this is this new Laurent expansion, which I believe is broadly interesting, far more broadly interesting than just this experimentation setup, right? And in terms of, as I said, what we're doing next, we're working on this policy optimization stuff, which I'm pretty excited about. You can use what I'm talking about to inform design in a kind of practical way. When people have thought about experimentation design over here, you get these optimization problems that kind of scale hopelessly in complicated Markov chains. And I think there's something we can do there. And then hopefully in a month or two, we get the permission to share the stuff that we've been doing with Python. That's it. Thanks, guys.